In the first part of the course, we learned to analyze continuous time systems and then used this knowledge to design CT filters. Next, we looked into how sampling and reconstruction works and how digital or discrete time systems can be analyzed. Now it is time to use this knowledge to design digital filters. And as a first step, we will look into the possibilities and limitations of digital filters. We will consider this specification of an ideal low-pass filter with cutoff frequency omega c, where all frequency components with frequencies between 0 and omega c are passed in the filter, and all frequency components with frequencies above omega c are filtered out or stopped by the filter. This implies that the frequency response h of omega is aperiodic. The fact that the specification is given for h of omega and not only its magnitude implies that h of omega is purely real. We also see that h of omega has the sharp transition between the passband and the stopband. And h of omega is equal to 0 for a range of frequencies omega. As we've seen for ideal continuous time filters, ideal discrete time or digital filters can also not be achieved. To see this, we will go through the properties of h of omega that we have marked here. For instance, if h of omega is aperiodic in the frequency domain, this implies that the impulse response h of t must be in continuous time. But since this time here we want to design a digital or discrete time filter with impulse response h of k, the corresponding h of omega of a digital or discrete time filter has to be periodic. As we have discussed for continuous time filters, if h of omega is purely real in the frequency domain, the corresponding impulse response in the time domain has to be symmetric, which means that it would be non-causal. But since we need to design a filter which has a causal and hence asymmetric impulse response h, we have to allow that the frequency response h of omega has a phase angle. When demanding a frequency response with sharp transitions, the corresponding impulse response in the time domain will have infinite range and hence be non-causal. But since for real-time applications we can only implement filters with a causal impulse response, we have to allow a transition band between the passband and the stopband of the filter. And also demanding that h of omega is exactly 0 for a whole range of frequencies can only be satisfied with a non-causal impulse response h. But since we require our impulse response h to be a causal function, we have to allow a stopband attenuation instead of having h of omega being equal to 0 for the entire stopband.